Welcome back to Machine Learning class. In today's session, we're going to apply the k-nearest neighbor technique to one data example, the iris classification example. So far, we have using the Scikit-learn to several different cases, including the linear regression and the logistic regression. By far, probably you have noticed that there's a pattern when we're using the scikit-learn for a machine learning model. In summary, there are 6 steps we need to follow through. The first step is we need to understand the data we're working on, then load the data into computer's memory. The second step is we split the data into train and test, and also data typically has x variables and y variable altogether. We also need to split the data into x and y. The third step is to use scikit-learn. We need to create an instance of a particular model we want to use by using the constructor function of the class in scikit-learn, which is implemented in Python in our case. The fourth step is with the training data, x and y variables, we're going to fit into a scikit-learn model that we have chosen. That's the fourth step, train the model. The fifth step is we'll make the predictions using the model that we just trained at step 4 using the training data, but now we apply the model to test the data. The last step is we want to evaluate the model's performance based on the predictions on the testing data and the actual values of those testing data we know ahead of time. In summary, those are the 6 steps that we need to follow through for each machine learning model that we're building and we're evaluating. Today, we're going to do that for the KNN, and we're also going to follow the same 6 steps. Here is the first step. We're trying to understand the data and then load the data into the memory. In today's case, we're going to work on the classification of iris. Basically, there are 3 categories, 3 different species in the iris data. There are 50 observations or instances for each species. The y variable in the data sets is the labeling, the class or the species for the 3 types irises we want to classify. The x variables we have only 4, or in other words, we have 4 features, which are sepal length, sepal width, petal length, and petal width. Basically, that's our data. If we click on the link here, we'll see how the data looks like. And here it is. Basically, the data from the web does not have any header. It's just in a format of comma separated flat file. But we know the order of the data. So the last one is the y variable, the class of iris, and the other 4 features are the x variables. And also with the data set, there are descriptions, so we know which column refers to what. Now let's continue with our data work, the step 1. And here just give you a sense what the 3 types of iris look like. We see the pictures of them. And also here we have the kind of a linkage between the picture to the feature. And here we have petal length and a petal width. And here we have sepal length and sepal width. Basically, we're dealing with 4 features and 3 different species of iris. That's the problem set, and that's the data set we're dealing with today with the KNN method. All right, here also look at some statistics associated with the data. Horizontally, each row is one feature or one independent variable. And vertically, the first column gives us the minimum of each x variable, and the second column gives us the maximum of each variable. Then we have a mean, which is the average of each x variable, and then we have the standard deviation, which describes how dispersed each variable can be. And lastly, we have a class correlation. The class correlation just measures one particular x variable in correlation to the y variable. If you see something really high for the class correlation, just means for that particular variable, for instance, petal length, here there's a class correlation of 0.949. It's really high, just means really you can tell that within each class, each species of iris, the petal length are similar to each other within the class. Here are just the numbers and the statistics of the 4 features. And next page, we'll see something else, and which you can make connection to this page, particularly the class correlation matrix we have here. All right, here we have the plots of features, and in total we have 12 plots. The first question is how to read those plots. Here it is. We have a color indicates the species, red, green, and blue. The reason we have 12 plots is we basically can choose any of the 4 features, any of the 4 x variables as our x-axis, right? If that case, we also want to choose another variable as y-axis. Since we already choose one of them, we have 4 choices for x-axis, and then we only have 3 left because think about the combination. We are doing 4 times 3, and we end up with 12 plots. And let's pick one, let's go column by column, right? First column, everything down here, literally we're making the sepal length as the x variable. But when we go down, this particular plot has sepal length as an x variable and the sepal width as y variable. When we go further down, this plot still have sepal length as an x variable, but now the y variable become petal length. Go down again, we still have sepal length as an x variable. Now the y variable becomes petal width. That is how it works. Similarly, you can think the same way for each columns on the page. Okay, now let's also check the last column. In here, you probably already figured out everything on this column has petal width as x variable. Since petal width is already x variable, I cannot have the y variable also as petal width, because if I do that, it doesn't give much information, right? So we'll pick something else as the y variable. In this particular chart plot, we're picking the petal length as a y variable. And here we pick sepal width as a y variable. And here we pick sepal length as the y variable. But everything, all the 3 plots on this column having the petal width as the x variable. That's the way how you read those plots, and that's also the reason why we only have 12 of them, because the combination is 4 times 3. Okay, furthermore, if now we know we have four features, four x variables in the data, we can use all of them to build the machine learning model. But let's say we want to cut them down to only two. What it means is rather than using all the four variables, we only pick two variables. If we want to make that decision, which two variables, x variables, or which two features we should keep, just give you a second, think about this. All right, here is my answer. If we only pick two variables, not four variables, I would suggest we only keep petal width and the petal length. And here's why. If we look at the petal width on this column, we know petal width is the x variable. The y variables can be different things, but what we can see clearly is the color, the same species are grouped together within the same class very tightly. We see red almost in this range, x variable range, and the green almost in this x variable range, and blue is in high end of the x variable, this particular feature, petal width. That just tells us petal width is kind of different between class and class, but very similar in the same class. So that's why petal width is a good feature to keep if we want to only keep two features. Similarly, petal width is the same thing. Everything on this column, we have petal width as an x variable, and we can see that is the different color, different species are compact together for this particular feature. It's very good to differentiate just using this particular variable as indicator or as predictor. And when we look at the other features such as petal width, we can see clearly the color are mixed together on the horizontal, on the x-axis. That just means across different classes, it's not so clear which species have certain values or certain range for this particular feature. They are mixed together, so it's not really good differentiator. Similarly, the petal length, you also see the color mixed up together on the x-axis. This information, the chart we're observing here, are kind of consistent with what we see on the previous page, the class correlation. As we can see here, petal length and petal width have very high class correlation, and the other two variables are not that high, even negative correlation. So basically, this class correlation metrics are consistent with our observation on the next page on the visual charts. Basically, that's my argument. If we only keep two features out of four, we should keep petal width and the petal length because those two variables are distinctive across the classes, across different species of the iris. Now we pretty much understand the data. We want to run this Python code to load the data into the memory. And here is the code. The first two lines really just helper line. They print out certain information timestamp. And this line is just give us the header names. The first data column is corresponding to sepal length, and second sepal width, and third petal length and petal width, and last column is class, because the text file, the data CSV file for the raw data does not have a header, but based on the data definition somewhere else, we know the order of the variables, what they are. And this simple line of code is the Python code of reading a CSV, the comma separated file, into the computer memory, into the pandas data frame. This is a key line we want to use. And the following two lines is we just want to make x variables the first four columns in the data. And because the last column, the class, is the y variable, we just separate our data into x variables and a y variable. With those few lines of code, we complete the data loading. Next step, we need to go through 2 through 6. The step 2, as we mentioned at the very beginning, we need to split data. Again, those lines, just for additional information, are not real work code. And this line does the real work. Basically, we have x variables and y variable already received from step 1. Now we want to split the data into train data x and train data test data x and train data y and test data y. This is the syntax you should use with Scikit-learn package. And here we're saying we want to make 33% of data going to the test, and the remaining data, 67% of data, go to the train. And there's a state called a random state. You can assign this value or some other integer values, because we're doing the data shuffling and we're trying to make it random. But in order to make every time when we do the data split, we can repeat our outcome, we want to use a seed, like fixed seed, as our input, so that we can get the same data partition when we call the data split function with the scikit-learn. The third step is we want to instantiate a scikit-learn model. Remember, scikit-learn implements models using the class concept. What we do here is basically we create one instance of this class. In our particular case, we're instantiating a k-neighbors classifier, and this is the constructor of the class. And now we're only passing one variable, which is we want to look at the 7 nearest neighbors in our case. That completes step 3. Step 4 is we want to train the model. And when we train model, and this line is the scikit syntax, we call the fit function. And in fit function, we put the x train variables and a y train variable. And this step pretty much completes the model training process step. Next, the model is trained. We can use the model to predict. And typically, we want to predict on the test data. We pass the test data x variables. That's step 5. Step 6, we already made a prediction with the test data on the particular model in choose. We have chosen. We want to evaluate the performance of predictions, how good they are. There are probably different metrics for the performance, and for the classifiers, we look at the 2 for now. One is accuracy. The other one, we want to look at the confusion matrix. And we also have this line of function we implemented ourselves for visualization, for a better plot for the confusion matrix. So this page, very, very few lines, but we go through all the remaining steps for building a machine learning model with Scikit-learn. All right. If we run the code, if we run the code we have seen before, we receive an accuracy of 98%. It's pretty high. Again, the accuracy is defined as number of correct predictions versus total number of predictions. And now we look at the confusion matrix. We also talk about the confusion matrix in the previous session when we talk about the logistic regression on the handwritten digit case. And here is how we read the confusion matrix. Horizontally, the x-axis represents the predictions. Again, we want to put each test data into three categories, three different species of the iris. And vertically, the y-axis represents the actual labeling in the test data. If we see numbers on the diagonal lines, that means our prediction line up with actual perfectly. Those are the correct predictions. Everything not on the diagonal line is misclassification. And here we see because we choose 33% out of 150 data, we roughly get 50 data observations in our test data set, and we get one misclassification. And that's why we get 98% accuracy, because we're right 49 out of 50, which is 98% accuracy. It's pretty good outcome with a very simple KNN algorithm we have achieved. All right, so far we have walked through the examples and how that works with the KNN algorithm. Now let's switch the topic a little bit. As we see that in the particular example, we are using the K of 7. We just said K of 7 when we invoke the class of KNN. But we also talked about it in our last session. What value of K to use in the KNN algorithm is something like hyperparameter we could optimize using the cross-validation technique. If we want to do that, here is what we can do. The first step is we create a list which represent the number of neighbors we want to look up in the KNN algorithm. And this line of code is just say, I only look at all the number of neighbors. And to do that, I get 1, 3, 5, 7, all the way up to 29. So this line will give us a list of all the integers between 1 and 29. And this CV scores is also list, which is initially just empty. Now here is the key part for the cross validation. We are now using the tenfold cross validation. So the outer loop is number of neighbors. Again, remember the neighbors is a list 1, 3, 5, 7. Basically, just going to loop through. First time we put the k equal to 1, then k equal to 3, k equal to 5, and so on and so forth. Within the loop, we actually keep calling the KNN classifier with different parameter, different number of neighbors. And then this with Scikit-learn built-in cross-validation function, which it does is it's kind of compacted loops. It will loop through our training data and tenfold. Every fold, 9 out of 10 go into the training, 1 out of 10 go to the validation, and the data rotates. Even though it's just one line of code, we are seeing here internally the Scikit-learn will rotate data, actually creates like 10 inner loops within each of the outer loop. Eventually, we're looking at scoring based on the accuracy, and then the average accuracy scores based on the tenfold rotation of cross-validation will be appended to the CV scores. Again, CV scores initially is empty list. each time when we vary the k from 1, 3, 5, 7, so on and so forth, we'll get one additional element into the CV scores. CV scores basically just contains the average accuracies from different choice of number of neighbors. Eventually, we do very simple conversion. We want to convert the accuracy into misclassification, which the relationship is just 1 minus accuracy is a misclassification rate. And those two lines of code are very trivial. They just figured out based on all different variations in the number of neighbors, which choice of k has the minimal classification, misclassification outcome, and then do some printing based on that. Eventually, we'll make a plot based on the number of neighbors choice as an x variable and the corresponding miss rate, which is again is a 1 minus accuracy. And all those lines of code will do the work and give us the plot just like this. Again, horizontally, the x-axis is number of neighbors that we vary in the outer loop, and vertically we got the corresponding misclassification from the inner loop rotation of the data through the cross-validation mechanism. And anyway, as we can see here, based on this setup, based on the data split, the optimal number of neighbors suggested by the cross-validation approach is 7. All right, now let me run my Python code, which will do all the steps as I just described in the lecture. Here is my code, which exactly does what I described just now. And let's click on it. Yeah, it's all done very fast because the data set has only 150 observations, pretty small data set. All right, let's go back to the slides. This actually concludes what I want to discuss with you using the KNN on one particular data set, the iris classification today. Now I want to talk about next week. Next week, we have no new lecture. And what we're going to do is we'll have in-class contest and presentation. Basically, there are two parts. The first part, in-class contest, we'll do the quiz together by using Kahoot. Probably we'll have time for 30 questions and do that in 15 minutes. The second part is students who are going to work on the case and present them case next week will do the presentation. I'm going to publish the case material just today. Basically, the case I want you guys to help me to solve is to use the KNN method to predict the handwritten digits. You probably remember we also used the logistic regression earlier to predict the handwritten digits. But now for your presentation, for your case, you're going to use KNN to work on that data set. And the context winner and case presenters will win prizes. That's all for today's class.